Hello everybody, this is the data processing video in the large-scale machine learning section of ML Expert. In the previous videos, we talked about how to get clickstream data into HDFS. Now that these messages from the clickstream logs or the clickstream records have been passed to the data nodes within HDFS, we have to now actually create features from these messages that we have. Let's say we wanted to predict whether or not someone would cancel their subscription. Let's say that the search functionality that we have on our very simple Flask web page is behind a particular paywall. For instance, Netflix requires that you have a subscription to use their app, and that search functionality within their app is embedded behind that paywall. Let's say that our app is similar. So we have a home page, and this home page may or may not have recommendations on it. And then there's a search functionality as well, where you can search for some particular content. So if we have that set up, and now we have all these messages from our clickstream logs indicating what did people search or what did they click on, our next job is to aggregate these different clickstream records in order to create features for our model which will predict whether or not users will cancel. If we can predict that someone may soon cancel, we can reach out to them, informing them of recent releases that we believe would be attractive to them. This would be an effort to make sure that they don't actually cancel. To start, this aggregation would involve counting how many searches per user. Why this is a useful feature is that if we see someone searching a lot, then we're able to see that this person is using the product a lot. If users are not searching as much, this could indicate that they may soon cancel. This is our hypothesis, and at least we need to build features in a model to determine if our hypothesis is correct. First, we'll aggregate how many searches each user does, and then we'll combine that from different clickstream events. Let's say that homepage had a list of recommendations that the user could scroll through. This is typically called a carousel. So the user would be able to select different recommendations from this carousel, and we'd want to collect that information as well because that is also usage information. The usage information could be helpful in predicting if someone may cancel. And finally, we may want to perform some sort of transformation on the records or messages that are present in our HDFS layer. If all of the records have dates attached to them, like a search event or a watch event, we may just want to have the nth month of the year instead of the entire date as a feature for the model to interpret whether or not it's a holiday season. Again, these are all hypotheses that should be verified with a model that we'll create. So all of these messages or these clickstream logs that we now have in our HDFS layer need to be processed in some way. The processing could be aggregation, joins, or transformations. The question is, how do we actually plan on processing these data? One idea is that we could just have a compute resource. Here we have a dual-core machine. We'll send these messages to some processor to process that message. So let's say that we were just transforming something. So let's say the message had a date, and we wanted to process that message to just have the nth month to featureize that record to be used later in some machine learning algorithm. And then we would send that message back to the data node, and then we would get another message to be processed. But there's a problem with this. Let's say that we get about 50,000 requests per second to our clickstream. So our HDFS will incur 50,000 new records every second. Let's say that we wanted to train a model on 3 months worth of that data. That would take about 4 hours just to transport all of that data to the processor. As well, when it gets to the processor, we have to actually process these messages, and if we assume that every message can be processed in 10 nanoseconds, then even with 2 cores, it'll take 45 minutes of processing on top of that. The whole process will take almost 10 hours just to analyze the last 3 months of data for some hypothesis that we had. This is a real problem because 3 months doesn't even incorporate seasonality. This could be retail sales changing with the seasons, or perhaps in our case, maybe people watch more Netflix in the winter. So how do we fix this? Well, we can steal from our idea that we've already had with HDFS in terms of disk space, but with processors now. So effectively, all of these data nodes would use these processors over here, which again are not local to these data nodes. It would send off their data to this remote cluster, and then the remote cluster would then store the data back in HDFS. The problem with this is we don't really know which processors have already been assigned work. Finally, how do we know which steps are done in a particular transformation? So let's say that we wanted to transform some data, then join some data. Well, we couldn't parallelize the transformation and the join because the transformation would have to be done before the join. In this case, we would have a really hard time to orchestrate all of this on our own. We're going to have to use some sort of tool here. So let's go over requirements again. We want cluster resource management. So we want to know, given a cluster of machines, how much CPU do we have left in total, how much RAM do we have left in total, so that we can assign more and more tasks to this cluster without overloading it. As well, we want computational dependency management. This is exactly what we talked about before, that if we want to have two operations done on some group of data, we need to make sure that if it has to be done in order, that it's actually done in that order. As well, if we don't care what order it's in, or it can be parallelized, then the tool should be able to take care of that as well. Locality just means that if the data that we need is on some processor, hopefully those processors are close together so we don't have to waste a lot of time transferring data across this cluster. Finally, we want to make sure that this tool will save all of the complete computations back to our storage layer. It would be even better if we didn't have to transfer all of the data from our HDFS to some compute cluster and back, because we would waste a lot of time transferring the information instead of actually processing the information. So we're actually going to use two tools here. One of them is Apache Spark, and the other one is Apache Yarn. Yarn, which is yet another resource negotiator, has a few components. One of them is a resource manager. The scheduler is a subcomponent of the resource manager, and it allocates cluster resources to whatever applications need it. And an application manager accepts jobs to be run on a particular cluster. A node manager, which will be present per node as opposed to the resource manager, in which there will only be one per cluster, it negotiates with the resource manager for resources requested by an application master. As well, it reports resource usage to the resource manager such that the resource manager knows whether or not to assign more work to that particular node. Finally, the application master, which was mentioned under the node manager, that's going to negotiate with the scheduler in the resource manager for more containers or more compute power. So here, containers are just an abstraction representing some RAM, CPU, or disk. Let's see how all these actually work together. So here, we're going to have a client who's using Apache Yarn. They're going to submit a job to a resource manager. The resource manager will start a container or an application master here on the node manager, and then that application master can then ask for more resources from the resource manager. The resource manager will look around to all the node managers around and say, this node manager has some resources available for a container, and so does this node manager. It will start those containers up for this application master, and then the containers will actually run the code that the user submitted to the resource manager. The user can periodically check in on the status of a job by contacting the application master. Finally, when the application has completed and all of the containers are done doing all of their computational work, then the application master will deregister the application with the resource manager, and that means the resource manager will then clean up all of the application masters and containers associated with that application, and the node managers will be free to take more jobs. So what does this do for us? So here, if we grouped 50 or so nodes together, or computers or machines, then we could think of their CPU and their RAM as being one giant computer. And Yarn will help manage the resources such that we can assign multiple instances of work to that cluster. Unfortunately, we still didn't gain computational dependency management. Basically, what we want is the ability to write code in one place and have some tool or software organize those instructions to be highly optimized and parallelized when possible. Effectively, we want the user to be able to consider this entire cluster that we have at our disposal to be a single computer, such that they don't have to write any specialized code to be run across the cluster. So how do we do that? Well, we can use Apache Spark. So Apache Spark has a few components as well. One is the driver. The driver is going to convert the user's code to a set of tasks. A task here is the smallest unit of work that Spark recognizes. As well, the driver will schedule these units of work, or tasks, across different executors. The executors are the ones who actually execute the code. Now, Spark also requires a cluster manager. That cluster manager is actually going to be Yarn. So Spark will use Yarn. It uses it to schedule jobs submitted to the cluster. Finally, the executor runs the task and returns the result to the driver. Let's see how this works. So the driver receives a job. The driver will verify the schemas, types, data structures. It'll optimize your code, and it'll form a physical plan. What this means is that it will make sure that whatever code you submitted, and in a little bit we'll look at what this code is, the driver will make sure the code is best optimized to be run in a distributed cluster. How it does this is it compiles your code down to an RDD DAG. An RDD is a resilient distributed data set, so that will be effectively the unit of data, and a DAG is a directed acyclic graph. So for instance, the DAG could say, join these two data sets, filter this data set, group these data sets together. These different steps or stages in the RDD DAG will be scheduled by the DAG scheduler. This is what we were talking about when we were saying, if we need to perform a transformation before we can do a join, or we need to join before we can do a transformation, this DAG scheduler will make sure that those things happen in order. Each stage has a series of tasks associated with that stage, so we need yet another scheduler to schedule those tasks within each stage. So after the driver creates these tasks and DAG schedulers, it will distribute these tasks out to executors, which will then return to the driver the result of that DAG. So how does Apache Spark fit in to Apache Yarn? Well, the driver is mapped to the application master, and the executors are just inside the containers. So here, this would be Apache Spark on Yarn. We would have the resource manager. The node manager would contain containers, which would have the executors, and one of the node managers would have the application master, which would be the driver of the Spark application. So now what we can have is these three boxes checked here. And additionally, we can install these tools, so Yarn and Spark, on our HDFS cluster, such that we don't have to move the data to anywhere else. It can all be done locally on the same cluster. Now, as always, we have to think in terms of high availability and fault tolerance. So the single point of failure for this combination here is the resource manager. So as we talked about earlier, you'll likely want some Zookeeper instance running, which will keep track of an active and a passive resource manager, and the passive resource manager can be set into a hot standby mode. All right, let's go ahead and see an example of Apache Spark on Yarn on HDFS. So the first thing I've done here is I've SSH'd into the name node of the HDFS cluster. You'll see that I'm actually using Elastic MapReduce to set up this cluster for me because it's far easier than setting up my own locally on my Mac or something. Now, the last time we saw the name node of our Hadoop cluster was in the web interface that we saw the different data nodes and we could browse the file system. That works perfectly well when those are the things that we want to do. However, if we want to use other software that's also installed on the Hadoop cluster, a good way is just to SSH into the name node. So for now, I want to run some Spark code on our Hadoop cluster. So let's go ahead and pull up a file which has some code already written for us. So here we're going to vim into PySpark example. And once we get a look at this file, we can break down what's going on here. This is specifically using something called PySpark. It's a way to write Spark code in the language of Python. So here we have to import Spark session. So every application, here our app name is MLExpert is going to have a session. Then that will give us this Spark object here. Let's say the first thing that we want to do is just read the partition from the topic MLExpert and read in all the JSON files that we have sent to it from our web interface, that simple Flask server that we've written. After we fetch the data from this partition, we simply want to show it and then stop the Spark session. This is a very simple file here. So let's go ahead and run this. So how we run this file is we can actually use a command that's in the bin of the Hadoop cluster called spark submit. It will submit this job to the Spark cluster. And after some time, we can see that it does in fact print out the data that we've sent to it from the front end. So just as when we went through the file system of Hadoop and we found a JSON file, we can access that same data file in Spark. And here we just pull that data and show that it did in fact get read correctly. If you recall, we just searched the term hello. So this could work well. One of the problems though is that it's harder to just be interactive with it. So instead we could use the PySpark interactive interpreter here, and this will spin us up a little instance in where we can do the same thing we did in those files, except now we will do that just line by line here with the interpreter. So what this did for us was it set us up with a Spark variable for free, basically. So that little bit of code that we wrote to initialize our own Spark variable, this one will do it automatically. So now we can do things such as this, and it will show us different progresses on what stages are happening. And once that's done, we can execute the same command that we did in our file, and we can see that we get the same result. So this is just another way to access and interact with our Spark software. Let's solve some more interesting use cases in terms of Spark. To do that, we're going to go visit another tool. This tool is called Jupyter Notebooks. What it does is it allows us to initialize a PySpark session in the same way that we did when we SSH'd into the name node of the Hadoop cluster. But in this case, this Jupyter Notebook is running on a separate instance outside of the cluster, and it's allowing us to contact the cluster in order to submit jobs to it. If you're curious, the glue between this machine and the cluster is called Livy. Livy provides an API to submit Spark jobs outside of the cluster itself. So the first line here looks very similar to what we did before. So here, if we execute this line, it will start the Spark application, and this is going to go through the same things that the PySpark interactive interpreter did. It's going to initialize a session for us such that we have access to a variable called Spark. Okay, so this finished up, and now all we have to do is show it. And we get the same result as we got before. So let's go ahead and see what happens behind the scenes here. So this is the Spark history server. We can see here that our MLExpert app that we named in our code and in our interactive interpreter over there, we can see that it has its own app ID. If we click that, then it will show the completed jobs under this particular instance. And more so, we can look at the stages that were associated with this particular Spark job. Let's go ahead and click on this one here. We can see the DAG visualization, and we talked about DAGs earlier in this video. We can also inspect other things on it, so we can see the duration, we can see the size of each record, things like that. If there's errors, we can see the errors or the standard out. It even shows which task was run on which node. In addition to this, we can go see all the executors that we have. So it looks like this cluster only has a single driver and a single executor, and they happen to be on the same node. This makes sense because I only have a one node Spark cluster here. Again, you wouldn't ever use this in practice, but for an example, it provides everything that we need. All right, let's go ahead and write a little bit more interesting Spark jobs. So here we're back at our Jupyter Notebook again, Now, instead of just showing something, we can actually rewrite things as Parquet. So we talked about Parquet earlier in the video series, and in this instance, this just goes to show how we would actually be able to write and read in different formats with Spark. So what we have here is a Spark session, which will grab all of the Parquet files from a search directory within HDFS. So here, after we run this command and we show that data in that directory, in reality, there would be far more than this to actually warrant a Spark cluster. But just to keep things simple, this is all that we'd have to have for now at least. So if we actually want to build a model which predicts if a user will cancel their subscription, and in this case it would be a Netflix subscription, say, then we would have all of their interactions with our search functionality. And what we could do is count the number of interactions that each user has with our search page. So how we would do that is by using a group by statement here. So we would have our data frame, which is df. We would group by the user ID and then just count how many rows there are. That would result in this section right here. We can see this user ID has 22 interactions with the search page. All the other users have an assortment of interactions as well. If you're more familiar with this notation here, so this is more SQL-like, it's not exactly SQL, but you can actually start a SQL context in PySpark, and you can run commands like this. I prefer to run things like this, but to each their own. So now what I want to do is transform the date time to be a real date that we can interpret as a date object for Python. And this is the line that's going to do that for us. And now that we have the dates actually calculable instead of just strings, we can do date arithmetic with them, and we can form different columns. So really what I don't want to know how many times a user has interacted with the search functionality. I want to know recently, have they used it? And even more recently, have they used it less or have they used it more? My hypothesis is that this would be tied to their probability of potentially canceling their subscription. So here what we'll do is we'll grab particular time intervals associated with their interactions. So here we're getting all the times the user interacted with the search functionality within the last month, week, and day. Finally, we're going to join all of those together so that we can have them in one particular data frame. So here we could see that this user, their monthly interaction over the last month at least, is 18. They've interacted 3 times in the last week and null during the last day. Here, null is equivalent to 0. We can do that here with this fill operation. So it'll just say user interaction counts NA fill. All this means is replace every NA with a fill of 0. And finally, let's show what that end result is. So now we can see all of the user ID counts of the times they've interacted with the search functionality over the last month, week, and day, and all of the nulls have been replaced with 0. All right, so finally, we can save our progress by just writing a Parquet file to a particular location. Here we'll just call it user interaction counts, and we'll make sure to include the time that this file was created. So now we have our features for our very basic model. We should actually join these with labels. So this file examines the labels instead of the features. So here we have a particular directory within our HDFS, which looks at the memberships per week of particular users. So again, here we're just transforming the string datetime to an actual datetime object that we can work with programmatically. And in that case, what we have now is a request path of membership. So there's a membership section of our website, and that membership section makes available to the user specific actions to their membership. So let's say a user ID is currently subscribed and they wanted to upgrade their account. That's the action that this user took on that page at this time. As well, you can downgrade or flat out cancel your membership. These clickstream records generated from the membership path are exactly what we need to form our labels of whether or not interaction data is tied to cancellations. So really, what I want to know is whether a user canceled their membership a week after the last interaction that I captured from them in the previous job that we looked at. So here, we're just going to create a new data frame where we're just filtering out the people who canceled their subscription. That would be these two user IDs here. And then we would export this and write it as well. In general, now that we have our features and our labels, so our features would be interaction data and our labels would be whether or not they canceled a week after the last interaction that we've measured by them, that now gives us the opportunity to create some machine learning model. Now, if the machine learning model that we create is very accurate, would be able to predict whether or not a particular user ID is about to cancel their membership within a week, that would give our team a week to reach out to them and perhaps convince them to up their usage of the product and perhaps change their mind about their cancellation. Now, finally, we would need to have another file or another job to be able to join these features and labels for our model, and we'll talk about that later. So now we know that by using Spark and Yarn on the HDFS cluster itself, we can conduct efficient data processing. This concludes the data processing video in the large-scale machine learning section of ML Expert. Thanks for joining, and we'll see you next time.